to session principles of estimation for multiple input, multiple output, orthogonal frequency division multiplexing, wireless communication. Okay, coming to today's session, wireless fading channel estimation in the pilot training based maximum likelihood and estimation. Okay, this is Karthik, assistant professor, Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Hyderabad. Okay, in the previous session we discussed wireless fading channel estimation. Okay, there we find out the some of the channels. We are taking the channel coefficient, but today topics we are considering the whatever the transmitted pilot symbols and also transmitted channel coefficient through the receiver section. That is also we can take it from the receiver symbol. We can also find out those one, and also mainly we are concentrating on the channel estimation. Channel estimation means we have to find out the channel coefficient, that is a H. Okay, in between the transmitter and receiver, in between the transmitter and receiver we are having the H. Okay, that is the channel. Okay, for the any transmitting or any communication you are considering the transmitter and receiver, in between the transmitter and receiver we have the channel or medium. Okay, that one we can find out, that is a channel estimation or channel coefficient. Okay, channel coefficient we can find out in this one. Okay, that is our main role, find out to the channel estimation in the transmitter and receiver. Coming to maximum likelihood estimation, that is a MLE. Okay, it is a method estimating the parameters, a probability distribution by maximizing the likelihood function. Okay, whenever you find out the maximum likelihood, okay, that will comes under the, whenever you can maximize the likelihood function, then only we know the maximum likelihood function, that is a MLE. Okay, that's why we have to maximize the likelihood function, then only we can go with the maximum likelihood function. And it comes under the some statistical models, that is observed data is a probable in the maximum likelihood function. Okay, the point in the parameter space that maximize the likelihood function is called the maximum likelihood estimation. Okay, that whenever it maximizes the likelihood function. Okay, that's here we considering the maximum likelihood function or likelihood function. Whenever you consider the maximum, it maximizes the likelihood function, so that is called maximum likelihood estimation. The logical maximum likelihood is both intuitive and flexible, and also it is a method has become a dominant means statistical interference. Okay, this we can concentrate on these parameters, that is in the transmitter section and receiver section. Here we having the transmitted symbols and receiver symbols. In between the transmitter and receiver we have to find out the channel estimation. Okay, if the likelihood function is differentiable, the derivative test for determining the maxima can be applied. Okay, in some case the first order conditions, the likelihood function can be solved explicitly, and for instance the ordinary least square estimator maximize the likelihood of the linear regression model. Okay, and also we can consider the under the some circumstances. However, numerical methods will be necessary to find the maximum likelihood function. Here we need the numerical method. That means we have to consider the observation model. Okay, we can consider the observation model. We can also consider the observation model. What is the observation model? For that we are considering the simple network. What is a simple network? The wireless sensor network we are considering here. That is a WSN, wireless sensor network we are considering. In that we are having the different nodes and different clusters. Okay, from the node we have to sensing the parameters. Okay, that is a parameters means that is a y equal to h plus v. Okay, y equal to h plus v. This is the output or received bits. Here this is the receiver section. Coming to this is the unknown parameters in the observation model. Unknown parameter. Okay, this is the noise. This one is the noise. This one is the noise. That is the Gaussian noise. Okay, third for that Gaussian noise we are having the mean is 0 and variance is the sigma square. Mean and variance. Okay, here we can maximize the likelihood function. Then only we are taking the maximum likelihood estimation. That is the MLE. That is MLE. that is the MLE, maximum likelihood estimation. Okay, coming to maximum likelihood estimation, we have the different properties. Okay, coming to different properties, we are considering the consistency and also functional invariance and efficiency, second order efficiency after correction of bias. Okay, we are having the unbiased condition also. Unbiased condition, but when we are get the unbiased means whenever you considering the estimation of the coefficient parameter and also two parameter, this is the estimated parameter, estimated parameter, and this one is a true parameter. Okay, this one is a true parameter. Whenever you consider in the those two, then we can go with the unbiased condition, but in this one we can find out the second order efficiency after correction of the bias, the relation to Bayesian interference and relation to minimizing the Kullback linear divergence and cross entropy. These are the properties. What are the properties for the maximum likelihood function, that is MLE? What are those? Consistency, we need some of the consistency in the over the signals, and also we have to different functional invariance will be there, and also we can find out the occurrence of the efficiency and the second order efficiency after correction for bias and relation to Bayesian interference, and also we can find out the relation to minimizing the Kullback linear divergence and cross entropy. Okay, coming to wireless communication, wireless communication network, wireless communication system. Coming to wireless communication system, what will happen here? Wireless communication system, we have the different factors. What are those? Equalization, diversity, and channel coding. These are the main factors for the wireless communication system. Here we consider the wireless communication system. The factors are the equalization, diversity, and channel coding. Okay, these are the three techniques that is used in the independently tend to improve the received signal quality. Okay, for the those three techniques, what are those three techniques? First one is equalization, equalization, and second one is a diversity, and third one is a channel coding. Okay, these are the three techniques for the improving the receive signal quality, and also why we go for the equalization. What is an equalization? What are the equalization parameters? How we can overcome the intersymbol interference? That purpose we are using the equalization. Mainly the equalization compensate for the intersymbol interference, that is the ISI. Okay, for that only we are considering the we are compensate the intersymbol interference by the equalization. Okay, whenever the ISI causes, that means it causes by the multipath fading. Okay, it causes the multipath fading, then we can get the these intersymbol interference. For that we need equalization. Then we can give the signal received signal quality. Then and also we can have the some coherent bandwidth of the radio channel. The intersymbol interference occurs and modulation pulses are spread in time. This is onto the equalization, and also we are having the equalizer within a received compensate for the average range of expected value channel amplitudes and delay characteristics. Further, we are also go for the equalization. Then you could consider the adaptive. Here we having the some adaptive equalizers. Adaptive equalizers. Okay, here we having the adaptive equalizer. Then we can consider in the training and tracking sections. Okay, there we have the training and tracking sections. It is also generally known as the time varying. The equalizer must be adaptive. Then we can have the channel is generally known as the time varying. Okay, this is considered in the channel equalization. There we having the some adaptive equalizer. There we are considering the training and tracking methods. Okay, coming to diversity, we are having the three techniques. One is the equalization, and second is the diversity, and third one is the channel coding. Okay, the first one is compensate for the intersymbol interference, that is the equalization. Coming to diversity is another technique. Okay, it compensates the fading channel impairments and also usually implemented by using two or more receiving antennas. Okay, this is in the diversity channel estimation. Coming to any equalizer, quality of mobile communication links improved without increasing the transmitted power and bandwidth. Okay, for example, no need of these three techniques. Okay, no need of these techniques. We can also improve the improve the signal quality, then increasing the transmitter power and bandwidth. Okay, whenever you need signal quality, then we can go with the increase the transmitter power or bandwidth. But no need of the transmitter increasing the transmitter power or bandwidth. We can go with the equalization, diversity, and channel coding. Then only we can also improve the signal quality. However, equalization used to counter the effects of the dispersion, that is intersymbol interference. The diversity usually employed to reduce the depth and duration of the fades experienced by the receiver in a flat fading or narrow band channel. Okay, this also comes under the diversity. We are having the different type of diversity techniques also there. One is a frequency 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 diversity, time diversity. Okay, then we have the different selective frequency diversity also will be there. Those are the different techniques for the diversity. Okay, in the comes under the fading, we are having the different types of fadings also there. One is the comes under the large scale fading and small scale fading. There we have the slow fading and fast fading. Okay, there we can consider the multi-path propagation by the occur of the fading. Okay, the diverse technique can be employed at both a base station and the mobile receiver. Okay, both the base station and mobile receiver. The most common diverse technique is called spatial diversity, where multiple antennas are strategically placed and connected to a common receiving antenna. When we are called multiple antennas, we are considering the MIMO technology. MIMO technology means multiple inputs and multiple outputs. Multiple inputs, multiple outputs. Whenever it go for the strategically, that is spaced connected to a common receiving antenna. That's that purpose we are go with the spatial diversity. Okay, these comes under the MIMO. Okay, these MIMO technology we are used in the our 4G fourth generation. Okay, in the wireless communication, we are go for the MIMO. Okay, coming to fifth generation, we are considering the MIMO and OFDM. Okay, we are consider orthogonal frequency division multiplexing. Okay, coming to one antenna sees a signal is null, and one of the other antenna also seek is a signal peak. Okay, and the receiver able to select the antenna with the base signal at any time. Okay, other diversity technique is including the polarization of diversity and frequency diversity and time diversity. Those are the other diversity techniques. Then you can consider the CDMA. CDMA is the code division multiple axis. Multiple axis. Okay, then that system often we are go for the rake receiver, which is provides a link improvement through the time diversity. Okay, whenever you use the rake receiver, it is also improvement the time diversity through the that particular signal that is in the CDMA system. Okay, we are having the different time diverse techniques: polarization diversity, frequency diversity, and time diversity. Okay, when one of the other antenna may be signal picker. For example, if you go with the MIMO technology, MIMO, there we having multiple inputs and multiple outputs. There we having in the transmitter section, we are considering the different multiple antennas. In the receiver section also, we are taking the multiple antennas in the receiver section. Okay, here what will happen? Here any signal is one of the signal is null, then the other signal will having the may it will take the signal is peak. That is a main advantage in the this technology, that is a MIMO, multiple inputs multiple outputs. Comes under the channel estimation. Our topic is the wireless fading channel estimation. That fading is the fading it compensate by the diversity. We are having the different diverse techniques for the polarization diversity, frequency diversity, and time diversity. Then we can compensate by the fading. Okay, in coming to channel estimation, we have to find out the H value. H is the channel coefficient. Channel coefficient. Okay, that we can find out easily. The process of finding the correlation between the array of complex numbers. In the left side, we are considering the complex numbers. Coming to right side, we are considering the array of complex numbers. Here we considering the some correlation between the array of complex numbers and left side, and coming to right side also we can take in the array of the complex numbers. In coming to wireless communication fading, there is a variation of the attenuation of the signal with the various variables. These variables include the time, geographical position, and also radio frequency. Coming to any fading, that is modeled as a random process. Okay, here we can take in the random process signals. If you are go with the probability, there we having the some prediction of the outcome. Prediction of the outcome will be there in the probability. Coming to in the fading, we are taking the some random process signals, and the coming to a feeding channel is a communication channel that experiences the fading. Okay, here you can see the large feeding. Here we having the feeding. You can consider the in this one. This is the large scale fading. This is the large scale fading. Okay, here the time interval in between two amplitudes we are having two time interval we are having the long distance. Okay, that is a large scale. Okay, coming to the small scale, we are having the rapid fluctuations. We are having the rapid fluctuations. Means this is a rapid fluctuations. What will happen in this one rapid fluctuations? Here the distance in between the time interval very low. Okay, the short distance will be there. Short distance in between the signal, that is a small scale path. Coming to large scale, we are having the large distance in between the amplitudes. And here we consider the transmitter separation, that is in the meter. Whenever the based on the propagation, we are having the received signal also in between the two traveling of the propagation of the signal in the transmitter section to receiver section. Coming to small scale fading, it is simply fading. It is used to describe the rapid fluctuations of the amplitude radio signal over the short period. Just now we discussed the signal over short time period. And travel distance is very short distance. Coming to large scale effects may be ignored, but if there is no short distance, it will having the some large distance. This one you can see. That way time interval is a very large. Coming to fluctuation and the rapid fluctuation in the small scale fading, here we having the small short distance, that is a short distance. Okay, sorry, short distance. Okay, short distance. Next in the fading is caused by interference between the two or more versions of the transmitted signal, which can arrive at the receiver slightly different times. For example, you are considering this is a transmitter and this is a receiver. This is a transmitter and this is a receiver. Here what will happen, whenever you can take in the one signal from the transmitter to receiver section, there is no interference. Okay, here there is no interference. There is no interference. Coming to, if you are generating the multiple signals from the transmitter, what will happen? Okay, like this will be there. Okay, what will happen here? One or more signals will be generated from the transmitter. Then here it causes the multipath fading, multipath propagation. This is called multipath propagation. Multipath propagation. This is in the transmitter receiver. Sometimes what will happen in the transmitter and receiver section, you will having the line of sight and non-line of sight. Okay, here we having the line of sight and non-line of sight. Coming to transmitter and receiver section, the signal passes like this. This is called line of sight, because in between the transmitter and receiver we don't have any obstacles, that is hills or mountains, we don't have anything. But coming to transmitter and receiver, we are having the any obstacle in between the transmitter and receiver. Okay, this is called non-line of sight. We here the signal will delay or signal strength will decrease. Okay, that based on the propagation. Okay, we are having the propagation that based on the reflection, okay, diffraction, that is also it caused by the these non-line of sight in the propagation. Coming to multipath, the most affected factors in the small scale fading. That one is the rapid changes in the signal strength over a small travel distance or time interval. Coming to random frequency modulation due to varying the adapter shifts on different multipaths. Coming to any time dispersion, also it caused by the multipath propagation delays. Okay, this is a way to we can find out the small scale fading signals. So that is the most important effects or factors in the fading. Okay, in the wireless systems, we are having the fading, that is a large scale fading or small scale fading. Show fading means in that we are having some particularly rainy, that is called show fading. It is due to the multipath propagation, and also it can induced by the fading. Then we can go with the affected the wave propagation. Sometimes it refer to shadow fading. Whenever you generate from the transmitter signal for the multiple signals, that is called multiple waves, then we can go with the shadow fading. Okay, you can observe here. Here the wireless systems fading can be either due to multipath propagation, that is called multipath fading. Here you can see this is a base station and this is a mobile station. Here we having the some multipath propagation. This is a path 1 and path 2 and path 3. Okay, here coming to difference of the path 1 and path 2, what will happen in coming to path 1, the path 2 distance will be high. Okay, that means the it will taking the time delay. Okay, the path 1 and path 3 also same. Okay, that is also in the shadowing method wave propagation. It is also known as the shadowing fading. In this one mainly we discuss effects of the receiver section of the signals in a code using multiple access. Okay, coming to types of the fadings means here wireless communication estimation. They'll be having the fast fading and slow fading. That is referred to the rate which is magnitude phase change imposed by the channel and the signal change. The coherence time is a measure of the minimum time required and the magnitude change. Okay, then we can go with the uncorrelated function, that is the change of the magnitude and also change of the phase. Then we can go with the these channel estimation. Okay, coming to slow fading, it arises when the coherence time of the channel large relative to the delay requirement of the application. Coming to any amplitude or phase change imposed by the channel consider roughly constant over the period of use. Okay, here we can consider the amplitude and phases changes. Okay, we having the unbiased function also. Unbiased means, okay, if we are considering the wireless sensor network, we are having the true parameter and estimated parameter, the estimated parameter and true parameter, then both are equal. When both are equal, that is called unbiased condition, unbiased. Okay, and also we are having the change of the magnitude and a change of the phase, then we can go with the biased condition. Coming to slow fading, we can use caused by the events such as show fading, where a large abstraction such as hill or large building. Then we can take in the main signal path between the transmitter and receiver, and then we can go with the shadow. Okay, coming to fast fading occurs when the coherence time of the channel small relative to the delay requirement application. In this case, the amplitude and also phase changes imposed by the channel varies is considered by the over the period of the use. Okay, coming to in a fast fading channel where the transmitter may take advantage the variation of the in the channel conditions using the time diversity to help the increase good communication temporarily deep fading. Although the deep fading any we taking the erase of the sum of the information transmitter use of an error correcting code coupled with the successfully. For that in the channel wireless communication system, we are having some uh, codes, code correcting methods and detective methods are will be there. That is a Hamming codes. Then we can consider the Hamming codes, convolution codes. Okay, there we can also find out the parity. In that parity, we can have the even parity and odd parity. Okay, in the transmitted beats during the Other time distance can allow for these erased bits to be recovered. In coming to slow fading the channel, it is not possible to time diversity because the transmitter sees the only single relation of the channel within the delay constraint. A deep fading, therefore, the lasts the entire duration of transmission cannot be imitated to the using coding. Okay, then we can see the single relation here, that is having some delay constant. If you go with the multiple relation means there is no time delay. Okay, coming to in the deep fade, in this we have the entire duration of the transmission cannot be measured using the coding. Then we can have that some instance of the time interval, it can allow to the bits recovered. Okay, then we can go with the fading channel estimation, and also we can go with the Doppler spread. Okay, mainly in the Doppler spread, whenever the user moving to the transmitter to receiver, whenever if for example here the vehicle is there, this is a vehicle, and here we have the receiver. Okay, this is a transmitter, this is a or a car or any vehicle, bike. Okay, whenever it can moving from the transmitter to receiver, there we having the different velocity. This velocity causes the frequency shifting the frequency, that is called Doppler spread. That is called Doppler spread. It is having the related quantity known as the Doppler spread. When the user is moving, okay, that reflected to the environment, the user velocity causes the shifting the frequency of the transmitter along the each signal path. This phenomena is called Doppler shift. This phenomena is called the Doppler shift. Okay, as the carrier frequency of a signal varied, the magnitude of the change amplitude is also varied. The coherence bandwidth measures the separation in frequency after two signals will experience in the uncorrelated fading. Then you can go with the flat fading and also frequency selective fading. Coming to in flat fading, we have to take in the coherence bandwidth of the channel, that will also can go with the larger the bandwidth of the signal. Then all the frequency components of the signal will experience the same magnitude of the fading. Okay, whenever you consider the frequency selective fading, the coherence bandwidth of the channel is smaller than bandwidth of the signal. The different frequency components of the signal, therefore, the experience uncorrelated fading. There we are considering the uncorrelated fading. When you can take in the different frequency components, okay, whenever you take in the different frequency component, then only we go with the uncorrelated fading. This is comes under the frequency selective fading. In the coming to flat fading, what will happen? The coherence bandwidth of the channel, that is larger than the bandwidth of the signal. Okay, this is a main. You can observe the bandwidth of the channel. The coherence bandwidth of the channel is larger than the bandwidth of the signal. Then all the frequency components signal will be experienced the magnitude fading. This is in the flat fading. Whenever we having the different frequency component, that comes under the experience is the uncorrelated fading. Okay, the estimation in the wireless sensor network, we are considering the wireless fading channel estimation. Then we go for the wireless sensor networking. There we can consider the transmitter and receiver. There we can take in the some sensor nodes in the wireless communication system. Now naturally wireless communication is take any place between the transmitter and receiver. Coming to in this one, the communication process can be between the transmitter and receiver. One has to estimate the channel coefficient, because the channel coefficient is unknown. That process is known as the channel estimation. How we can find out the channel estimation means, this is a transmitter and this is a receiver. Transmitter and receiver, we are having the pilot symbols. We are having the pilot symbols. Okay, the main concept of our today class is this is the pilot symbols of in the transmitter section. This is the pilot symbols of the receiver section. Okay, here in this transmitter we are having the transmitter antenna. In this one we are having the receiver antenna. In this we are having the transmitter antenna. In this one we are having the receiver antenna. Okay, in between transmitter and receiver we are having the channel. This is the channel. Okay, we can find out the parameter of H. This is the channel coefficient. Channel coefficient. Okay, from this one we can find out the transmitted symbols and receiver symbols. Okay, in this one transmitted symbol we can find out the symbols of the transmitted symbols and the receiver symbols. They be having the different one. This is one x of 1, x of 2, x of n. This is in the transmitted pilot symbols. Transmitted pilot symbols. Okay, coming to here y of 1, the corresponding outputs related to the pilot transmitted symbol. We are considering the y of 1, y of 2, and y of n. This is the received pilot symbols. Okay, in the previous session, coming to the same wireless fading channel estimation, we are taking the joint PDF. We are considering the giant PDF means that is a giant probability density function. We are also find out there that is in the f of y. Okay, and y of k we can also find out in this giant probability density function. Then also we can go with the individual functions. Okay, in the unknown parameter, that will also we can see the beginning of the communication. The h is basically which is a channel coefficient. This is a channel coefficient. H is a channel coefficient. Therefore, the H has to be this estimator, which is the central focus of the estimation. And also, we can take in the important factor of the wireless communication system, that process. Okay, whatever we are taking the channel coefficient, that process of estimation of H, that termed as the channel estimation. Okay, the process we can find out the estimation of the H. This process is known as the termed as a channel estimation. The process of estimating the this channel of coefficient is H. The term is channel coefficient, channel estimation. And also we can find out the unknown channel coefficient. Okay, in this one we know the known factor and unknown factors. When take place between those that unknown parameter, it takes between the transmitter and receiver. Okay, this process also known as channel estimation. Okay, here we can consider the some simplest scenario that we can find out in the channel coefficient, that is H, that is estimated in the real parameter. Okay, coming to here the developing of the framework, we are taking the some complex parameter estimation. We can also find out the f of y of k and y of k equal to 1 by under root 2 pi sigma square. And also we can take an e power of 1 by 2 sigma square y of k minus h of k whole square. Okay, this is in the PDF probability density function. There we can find out the individually probability density function. Okay, here we are considering the individual probability density function. For that we are taking the transmitted pilot symbols x1, x2, x3 and xn, so on. Coming to here also we can consider the corresponding symbols y1, y2, y3 up to so on y of n. This is the x bar, that means the x vector, and this is the y bar, that is a y vector. Coming to this x bar, x vector is in the transmitter symbol, y bar is the transmitter, that is comes under the receiver symbols. Okay, like that we can find out this one. Okay, however we take considering the this is the observation model, y of k equal to h of x of k plus v of k. Here this is the received symbol, and this is the channel estimation. This is the transmitted symbol, and this one is a noise, that is a Gaussian noise. Okay, in this Gaussian noise we are find out in the previous sessions that is a mean is 0, that variance is a sigma square. Come to here we are having the h of k and sigma square. that is a mean and variance for these received symbols. Okay, this is a scenario we can taken for the training symbol based channel estimation. Okay, coming to here, we are considering the f of y of k, that is the y of k equal to 1 by under root 2 pi sigma square e power of 1 by 2 sigma square y of k minus x of h of k whole square. Okay, here this is the unknown parameter in the channel estimation, unknown parameter. Okay, this is a unknown parameter. Okay, from in this one, this is a pdf, we are go for the individually means 1 by under root 2 pi sigma square e power minus 1 by 2 sigma square, that is in the y of 1 minus h of 1 whole square. Okay, and also we can multiply with the another symbol means same 1 by under root 2 pi sigma square e power minus 1 by 2 sigma square. Here we consider the y of 2. Okay, another received symbol we are considering here, that is individually h of 2 whole square, so on into 1 by 2 under root 2 pi sigma square e power minus 1 by 2 sigma square y of n minus h of n whole square. This is in the function of the unknown parameter in the likelihood wireless channel estimation. Okay, further we are taking the, this is in the individually pdf, that is a probability density function. This is a unknown parameter of the function, that h always h is go for the unknown parameter in the likelihood function, okay, of the wireless channel estimation. Then we can go with the, just now we find out the x bar and y bar, that means a received vector, received transmitted pilot vector, sorry, a transmitted pilot vector and received pilot vector is a y bar, and transmitted pilot vector is a x bar. Okay, then we can consider the y bar equal to y of 1, y of 2, so on y of n. Then this is the output vector of the observation, output vector of observation. Okay, this is the output vector. Okay, we know the input vector means x1 x2 and after so on xn. Okay, there we can find out the natural algorithm, that is a y bar h natural algorithm p y bar h, this one. Okay, from log likelihood, this one is the way taken from the log likelihood, then we can substitute the minus n by 2 natural logarithm 2 pi sigma square minus 1 by 2 sigma square summation k equal to 1 to n y of k minus x h of x of k whole square. Okay, this is for the naturally that is a probability function, natural logarithm. Then we can mainly from this one we can find out the maximum likelihood estimation, that is a MLE. Okay, further we can compute purpose we are taking this one. Okay, further we are also considering the some differentiation. Okay, for we can adding the some differentiation to the this particular value, then we can having the minus 1 by 2 sigma square equal summation of k equal to 1 to n y of k. We are considering the, we can recall x of h of k. Then when we are applying the differentiation here, what will happen here, we can considering the differentiation of the this value by dh, we are taken from the differentiation for this value, we can having the minus 1 by 2 sigma square summation of k equal to 1 to n y of k minus h of x of k. Then we can write this one into minus x of k equal to 0. Okay, then also we can write summation of k equal to 1 to n x of k we can take multiply with the both. We can write y of k minus h of x of k equal to 0. Then we can also compute this one, summation of k equal to 1 to n x of k y of k equal to h summation k equal to 1 to n x square of k. We can write like this. But we have to find here, we have also find out h hat, that is the estimation parameter. Then we can also write summation k equal to 1 to n x of k y of k by summation of k equal to 1 to n x square of k. Okay, this is our maximum likelihood estimation of the h. Okay, this is a MLE of h. Okay, we can find out this one. Next one, we can find out, we are considering the y bar values and x bar values. Then we can write y of 1, y of 2, and y of 3, so on, y of n. Okay, this is in the received section pilot symbols. Coming to here, we can take the x of 1, x of 2, x of 3, so on, x of n. Okay, this is in the received transmitted pilot symbols. This is a received pilot symbol y bar, and this is a x bar. Here we can take in the, this is a observation vectors. Okay, in the both the case we are going to find out the observation vectors. Okay, from that we can write x bar equal to y bar. Okay, this is a y bar and this x bar. Then we can write x of 1. Okay, we can write x of 1 into x of n. Okay, and we can having the some vectors y of 1, y of 2, and so on, y of n. We can consider like this. Then we can write this one, summation of k equal to 1 to n x of k in y of k. Then this is a equation number 1. Okay, then we can write x minus transpose x bar equal to x of 1 x of n, coming to this one, transpose x of 1 x of n. Then we can also write summation of k equal to 1 to n. This is a x square of k. This is a equation number 2. Okay, in the previous one we are considering the, this one is the y of 1, y of 2, so on, y of n. Okay, like that we have taken, that is a summation of k equal to 1 to n by x of k, y of k 1. Okay, then we can write equation number 2. Then we can substitute those values in this x, the previous whatever we taken from this one. Here we can take in this estimation of the maximum likelihood estimation of the h. Then we can substitute the equation 1 and 2 here. Then we get the k equal to 1 to n. This is the previous one, x of k, y of k by summation of k equal to 1 to n x square of k. From the equation 1 and 2, we can write x transpose x y bar by we can take the x transpose and x bar we can write. We can write, and also we can take in the, this maximum likelihood estimation of the channel estimation. For the to extend purpose, we having the h hat equal to x Hermitian. Here we have taken the Hermitian, that is a y bar by x Hermitian x bar. Okay, we can also take in this maximum likelihood estimation of the transmitted symbol and also received symbol. Then this is the our required appropriate equation for the wireless feeding channel estimation. This is the h hat. This is our channel estimation. Okay, in the next session we can also discuss the wireless feeding channel estimation of the downlink scenario and uplink scenario. Okay, that we'll discuss in the next session. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.